Good afternoon, everyone. Welcome to week 8 of the doubt clearance session on regression analysis. My name is Shreya, and today I'll be discussing concepts discussed during week 8 lectures and a few problems associated with that. So, let's get started. So, in week 7, we learned a lot about influential variables and leverage points, which are essentially outlying or sort of outliers in terms of x or the y variable, that is, in terms of the predictor or the response variable. Now, just to brush up the concepts, we first learned what we mean by influential points. So those are points which are, if this is my x and this is my y and this is my scatter plot, let's say, then something which is, this should have been the regression, which is the original one, okay? Or rather, if this is the expected fit in a, where the relationship between x and y is this, if we have something like this in the data set, where this data set has unusual x and it has unusual y, and it distorts the regression line. So this one, in the presence of this point, this line tilts towards a little bit here. So then this is an influential observation. Okay, and on the other hand, if this is also a leverage point because the x value is unusual. Okay, so mean of x should be somewhere over here. Usually mean should lie over here, or this is where I would say the range of x should be, but this is far from that range, so this is a leverage point. Okay, right. So the last week we learned how to identify. The last week we learned how to identify leverage points. So we learned something which is called, known as the H or the hat matrix. Okay, so hat matrix is nothing but, if this is my multiple linear regression, that is y equal to x beta plus epsilon, then and if these assumptions hold, that expectation of epsilon is 0, variance of epsilon is sigma square I, and also we assume that epsilons are if this is the assumption, if these two hold, then we can find out that beta hat by OLS is X transpose X inverse X transpose Y. Alright, now then Y hat is actually X beta hat, that is X into X transpose X inverse X transpose Y, which is actually HY. Alright, and we also learned a few more properties, that the residual is actually nothing but I minus H into epsilon, and variance of the residuals is nothing but sigma square into I minus H. Okay, so the one thing to note here is that the variance of errors is sigma square I, but variance of residuals is sigma square I minus H. So epsilons are uncorrelated by assumption, but residuals are not. Alright, okay, so coming back, HII is nothing but diagonal of H, this is the ith diagonal of the hat matrix. HII is nothing but the it's nothing but the ith diagonal of the hat matrix, and this is the one which would be used to determine whether any observation is influential or not. So HII lies between 0 and 1. Okay, and apart from this, so here we are going to learn in this week's lecture, we are going to learn how to test for a leverage point, okay, using this thing. So this week we learned testing for leverage point. Okay, so HII, since it's the ith diagonal of hat matrix, what does it essentially mean? HII is actually xi prime into x prime x inverse xi. Okay, So if we X matrix that we were talking about over here, this is an n cross k matrix. Let's say if we write it like this, xi prime, x2 prime, xn prime, okay, where each xi prime is a 1D vector, where let's say this is the intercept term, this is the x11th term, this is x12th term, this is x1kth term. Okay, so let's say, let us consider that example of y equal to x beta plus epsilon, where beta are where y is the price and these betas are predictors of price of a house, let's say. Okay, predictors of the said price. Okay, so then this could be the predictor, the variable on predictor 1, variable on predictor 2, and variable on predictor k. Okay, so if we parameterize it like in this manner, then HII is actually xi transport x prime x inverse xi. In essence, it is actually this one is this variable here, x prime x inverse, is sort of a normalizing thing. So this, what this is measuring it, so this part is actually catering to the standardization. Okay, and this actually means xi prime xi, this means the, so HII implies the standardized distance of ith observation from the center of a center on the x coordinate. So given that it's a kth dimension plane, xi prime xi is the distance of the ith observation from the center of the x coordinate plane, because this is already done this standardization. Now once we know what HII is, we can say, we can formulate this thing. If HII is greater than 2h bar, then we say that, so that is, if the ith HII associated with the ith point is greater than twice the mean h bar, the mean of the distances, then we can say that yes, ith observation is actually a leverage point. Okay, so h bar is nothing but, this is summation I equal to 1 to n HII divided by n. Okay, so HII is, summation HII is actually nothing but trace of h by n, and this, since h is idempotent, trace of h is equal to rank of h by n, and rank of h is k by n. Alright, because it's a full rank matrix. We have to remember h is idempotent, which implies that h square equal to h. Okay, so if we find any observation, ith observation with the associated HII greater than 2h bar, then we can say yes, the ith observation is a leverage point. Okay, and then we also learned about a few plots which would give us, so last week we also learned about so I'll write it over here. We learned about standardized residuals. Okay, and how do we calculate standardized residuals? So if we denoted it by di, this is actually ei, the ith residual, divided by square root of ms residual. Okay, and we also learned about studentized residuals. Okay, and studentized residuals are what? They are nothing but Ri is equal to Ei by, instead of using only ms residuals, we will also use ms residuals into 1 minus Hii. Okay, so why this 1 minus Hii? Because we have shown that variance of Ei is, so we showed variance of E is I minus H into sigma square. So then from here we can see that variance of Ei would be sigma square into 1 minus Hii, and sigma square hat is from any regression model is actually the ms residual. So we learned about standardized and studentized residuals, and we also learned their relationship, that the Ri is usually greater than di. Okay, because this denominator is smaller. So Ri, studentized residuals, are usually larger than standardized residuals. Okay, and we also learned a little more about press residuals. Okay, alright, so press residuals are what? They are nothing but residuals. So if Ei is actually residuals, if Ei is actually ith residual after fitting the entire data yx, then Ei or Ei is actually the ith residual after fitting y and x, leaving out the ith observation. Okay, and we showed that Ei is equal to the residual divided by 1 minus Hii. Okay, and if so in this case as well Ei is usually greater than Ei. Alright, Fine. We also learned quite some about different kinds of plots. Okay, the first one was residual plot. Okay, and the requirement is for a good fit is that there shouldn't be any pattern. That is, we want a random scatter about 0. This is the ideal plot that we would want if we have to comment that okay, we have made a good fit for the data. So what do? We plot the residuals ei on the y-axis and yi hat, the predicted response variable, and if this is equal to 0 line, we want a random scatter over here. Alright, so we'll come back to this later, but before this everything else, last week we also learned about influential, as I was saying, influential points. So this week we learned how to test for these. Okay, so coming back here, there are too many ways to test for this. Okay, so this using H is for leverage, as we have seen, and these would determine if it is an influential point or not. So we'll discuss these statistics one by one. Alright. Fine. So the first thing that we can use to test whether a point is influential or not is by using Cook's distance. Okay, and how do we calculate Cook's distance and what is it? We are going to learn very shortly. So Cook's distance is nothing but finding out the distance between predicted, by distance I mean the Euclidean distance, between predicted y without ith observation and predicted y with ith observation. Okay, so what it essentially is doing, let's say it is finding out how much of a difference in the prediction can be attributable to that ith point, and if the ith point is actually influential, then this distance should be significantly large. Okay, so in order to properly formulate, di is actually yi hat minus y hat transpose yi hat minus y hat, and this is scaled by k into ms residuals. Okay, so this can be notationally written as summation y summation over j y I j minus yj hat whole square divided by k into ms residual. Okay, so if di is much larger than other, then we can say that the ith observation is influential. All right. So in order to calculate this, we'll need two set of vectors. We would need yi vector that would have, let's say, y1 predicted, y2, y1 predicted, y2 predicted, yn predicted, and also y hat, that is y1 predicted, y2 predicted, and yn predicted. Okay, so this is Cook's distance, which will help us to assess whether the ith observation is influential or not. All right, the next one that we can use is actually df fits. Okay, now df fits I is given as yi hat minus yi hat divided by root over ms residual I into hii. Okay, so here we are calculating ms residual based on that model which is leaving out the ith observation. Okay, so yi hat is the fitted value of yi obtained without the ith observation, and ms residual I is the associated ms residual in that model. And the cutoff is if df fits I, if the absolute value of df fits I is greater than 2 into root over k by n, then we say that this is, then we can conclude that the ith observation is an influential point. All right, so this was how we can calculate, how we can assess if a point is influential using df fits. Apart from using df fits, we also learned how to use df betas. Okay, so df betas is actually, so what does df fit indicate? Df fit indicates how the fit changes, or how, I would rather say, how the prediction changes with or without the ith observation. Now prediction, whenever the prediction is changing, the prediction is changing because of changes in the regression coefficients. So if we really want to assess that how the regression coefficients change with an influential observation, we will assess df betas. Okay, now for the jth regression coefficient, df beta ij, so I is actually for individual and j is for the jth coefficient. Okay, so this will be equal to beta hat j minus beta hat j removing the ith observation divided by root over ms residual I into x prime x inverse the jth value, that is the jth diagonal element. So what's the difference? Here we had y hat predicted minus yi and hii, but here we would have similarly the same thing in written in terms of betas, and instead of hii we would have x transpose x inverse jj. Okay, and if we see that, so if we see that df beta ij absolute value is greater than 2 by root n, then we can say that this ith observation is an influential observation. Okay, so this was about how to find out whether these are influential, any point is actually an influential point or not. And we also learned about the press statistic. So a little more here, what did we learn about press statistic? So last week we learned about press residuals. Okay, so this is actually press residuals are what? EI, which is equal to yi minus yi hat. Okay, now press statistic is actually summation ei square, that is I equal to 1 to n. How much overall the residuals change if we remove observations one by one. Okay, and this one actually goes to summation I equal to 1 to n yi minus yi hat whole square. Okay, and this one, since we know that ei equal to ei by 1 minus hii, we can directly substitute it over here, and that would be summation I equal to 1 to n ei by 1 minus hii whole square. And this is nothing but the press statistic. Okay, fine. Now coming back to the cutoff criteria, how do we assess that the press statistic is actually how can we use the press statistic to assess whether there are inferential points or not? Okay, or how can we use to assess if the fitted model will predict new observation well. So if we see that press is much greater than SS residual, then the answer is it will not predict well, not well. But if not, then maybe, prediction is well, if this is at par with the SS residuals. But if the press statistic is way more than the SS residuals, then we would say that no, this model, whatever we have fitted in the presence of those inferential points, will not predict the new observation well. Alright, so this was about leverage and inferential points, and then we learned about a few plots in the last week, and we'll build on those plots and some intuitions in this week, and that would help us in understanding transformation of variables. Alright, so coming back to the plots that we learned last week, the first one was the residual plot, as I was saying over here. So this is what we would want. Okay, this is the ideal case, but we sometimes see points like this. Sometimes we see that here, if we plot yi hat on x-axis and the residuals on y-axis, we can sometimes see that as yi increases, the variance or this residuals, they seem to move away or scatter further, giving us an illusion of this open of a funneled shaped plot. So here ei is increasing with yi prime. Okay, so this is something not wanted. Okay, because this violates, if this is the situation, this is sort of violating the assumption that variance of the residuals should be sigma square I. It should be constant. Okay, so given now this one is that stage of the model fit where we have actually taken care of influential points and leverage points. So we know that the fit in that sense is sort of good. Okay, now the last step is to not last step but few of the penultimate steps is that we plot a residual plot, and we expect to see something like this, but instead if we see something like this, then this is actually violation of the assumption of homoscedasticity, that is the variance of the errors remain constant. But here we don't see that pattern. Okay, we see that as y increases, ei is also increasing. Similar pattern will be observed if with increase in yi hat, the variance initially, let's say this was the errors, but as yi is increasing, this thing is decreasing. So we see something like this. So both of these are unwanted situations and we don't want that. So in cases where such situations can arise, we can use some transformation to make the variance stable. So those are usually known as the variance stabilizing transformations. Okay, and if we also observe some sort of pattern, let's say something like this. If we have yi hat here and ei, the residuals here, and this is the e equal to 0 line, and we see some sort of pattern over here. So this looks like this could be a quadratic fit or something. So here we can see that maybe from this pattern we can say that maybe x square terms are needed in the model. Alright, so drawing motivation from here, from the previous one actually, we will look into some of the variance stabilizing transformations, okay, that we learned in this week. And also since we are testing the assumptions, we also learned about another plot, which is the normal probability plot. Okay, so the assumption for testing that was that the epsilon i's, they follow normal 0 sigma square for all I equal to 1 to n. Okay, now if we get from here, if we get the residuals e1, and ordered them, okay, such that this is the ordered residual, then we plot EI against PI. Okay, PI is nothing but cumulative probability, and this plot of EI versus PI, if we see that the values are scattered about y equal to x, then we can say that okay, this is normally distributed. Okay, but if we see deviation from this QQ plot, or not really QQ plot, deviation from this normal probability plot, then we have to apply some sort of transformation. So what are the transformations and what to apply in which scenario, that is something that we learned this week. Okay, so we'll discuss more on this thing, but first let us do a few problems and then we'll move on to the transformations. So the first question that comes here is this thing: what does a normal probability plot help you to test? Okay, so what does it help us to test? It helps us to test the normality of residuals. Okay, moving on. So here the table below represents the diagonal element HII of the hat matrix while fitting a multiple linear regression model y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon on 20 observations. So given that SS residual is 109.95, is observation 5 an outlying observation in terms of its x value? Okay, so this question, outlying observation in terms of its x value, is actually the question is it a leverage point or not? Okay, so how do I test that? So in order to test for leverage points, we have to see if HII is greater than 2h bar. Okay, now let us just calculate h bar and find out whether it is a leverage point or not. Okay, so if we calculate h bar, how h bar is how much? It is summation HII by n. So let us just calculate how much is h bar is. So this would be 0.201 okay, so 0.201 plus 0.059 plus 0.372 plus 0.111 plus 0.248 plus 0.129 plus 0.156 plus 0.096 plus 0.115 plus 0.096 sorry 0.115, then 0.110 plus 0.120 plus 0.178 plus 0.109 plus 0.148 plus 0.333 plus 0.095 plus 0.106 plus 0.197 plus 0.067 plus 0.050. This is how much? This is 3. So this would be, if so, this is actually 2h bar is actually 2 into 3 by 20. So this is actually 0.3. And HII for the fifth observation is 0.248. Okay, so 0.248 doesn't exceed 0.3, so therefore the answer is no. Alright, okay, so moving on. Consider the data in problem 2 is observation 15 and outlying term observation in terms of its x values. So H15 is actually 0.333 and 2h bar is actually 0.3. So HII is greater than 2h bar, therefore yes, it is an outlying observation. Okay, moving on. So we'll consider the data in problem 2. In order to identify possible influential observations, the total number of DF fits to be computed is how much? So DF fits, if you remember, this was yi minus yi hat divided by root over ms residuals into HII. Okay, this was what we had learnt about DF fits. Okay, now this yi hat is actually fitting y and x without ith observation. So therefore, the total number of DF fits to be computed is actually total number of DF fits to be computed always equals total number of observations. So the answer is C20. Alright, moving on. So if we consider the data in problem 2, in order to identify possible influential observations, the total number of DF betas to be computed is how much? So let's just find out how many. So here DF beta is actually beta I hat minus beta ij to beta ij hat by root over ms residual into x prime x inverse jj. So here we see that this is the beta value for the jth parameter, removing the ith number of observations. Okay, so I is actually 1 to 20, and j, from this equation we can see how many parameters are there, 1 2 3. Okay, so j ranges from 1 to 3. Therefore, number of DF betas is actually, why? Because this is beta naught, beta 1 and beta 2. Okay, so therefore total number of DF betas that have to be calculated is actually 20 into 3, that is 60, and that's the answer, D. All right, this is the answer, required answer. Okay, moving on. Variance of E2 equals how much? So if you remember, variance of E is I minus H into sigma square. So variance of E2, EI, would be 1 minus H22 into sigma square, and that's the answer. Okay, moving on. When we fit the model y equal to beta naught plus epsilon, that is no access to a set of data, we get how much? So if beta naught is epsilon, then r square should be because r square is what? R square is proportion of variance in y explained by x's. Now in the absence of x's, r square should be 0. But how do we do this formally? So if we have to find out beta naught hat, we have to minimize summation y I minus beta naught whole square, I equal to 1 to m. Okay, this is the this is the actually residual sum of square, which we need to minimize in order to find out beta naught hat. So so this one we can write it as the residual, SS residual, in the sense yi hat minus beta naught, this thing. Okay, yi minus beta naught hat. This is the sum of squares due to residuals. Now if we differentiate the sum of squares due to residuals by beta naught, so d beta naught hat into ss of the ss residuals would be summation 2 yi minus beta naught hat into minus 1 I equal to 1 to n, and equate it to 0. So that implies that beta naught hat would be, so 2 and y is gone, that would beta naught hat would be actually y bar. Okay, so If beta naught hat is y bar, then SS residual is actually summation yi minus y bar whole square, which is actually SST. Therefore, if we think of this decomposition SST equal to SS due to regression plus SS due to residuals, and my R square is actually SS. So from here we can say that since R square is nothing but SS due to regression by SST, here since SS residual is entirely SST, here SS residual is actually 0, and that's why we can say that R square is equal to 0. Is it okay? Then let's move on to the next one. So the question says that let y be the vector of response values and e be the vector of residuals, then e prime y equals to how much? Okay, so e prime y is actually 1 minus r square into SST. Excuse me. Okay. All right. So now that we know this, we'll move on to learn about transformation of variables. Okay, so what did we, so from here, from these plots, we sort of understood when to use transformations, when these certain conditions seem to be violated. That is the point where we should go ahead and use some sort of model transformation so that the usual OLS assumptions are no longer violated. Okay, so the thing that we learned is these violations may occur when y so in cases where sigma square, let's say that expectation of y is mu and variance of y is sigma square, okay, should be independent of each other. Okay, so ideally should be independent. But let's say we have this case where sigma square is some function of the expectation. Okay, so this could lead to problems. Alright, now how do we go about transformations so that this problem is circumvented? Okay, so the thing is, we have to do some sort of transformation on the y variable. Okay, and this one, let's say f of y is that transformation, so we need to fit u in that model such that the usual good assumptions and nice properties, all of them hold. Now using Taylor series approximation, okay, so how does this work? So if we have, let's say, fx, then if we assume that fx is infinitely differentiable in a neighborhood of a, where a could belong to the set of real numbers, let us focus on real numbers for now, then we can have fx as, we can write it as f a plus f prime a by 1 factorial into x minus a plus f double prime a x minus a square by 2 factorial and so on. Okay, so this is the Taylor series approximation. Now u equal to f of y, this if we expand and approximate with a as mu, then we can write fy as f mu plus y minus mu into f prime mu by 1 factorial plus y minus mu whole square f double prime mu by 2 factorial plus so on. So this would be the actual Taylor series approximation. Now retaining up to or approximating up to the first order differential, okay, we can write fy as f mu plus y minus mu f prime mu by 1 factorial. Okay, retaining up to the first order. So then variance of u would be how much? F mu is a constant with respect to mu, so this with respect to u, so this is a constant, so variance of a constant is 0, and variance of y is here, this is the only random term over here, that is this y, and mu is constant, f prime mu is also a constant, it's a function of a constant, so it should be a constant. So Here we can write it as f prime mu whole square. Okay, since this is a scalar quantity, and variance of y minus mu would be variance of y. Why so? Because variance remains invariant to change of axis. Okay, invariant to translation. So variance of u would be this thing. Okay, and we can write it as f prime mu whole square into variance of y was what? It was actually sigma square, which is actually g mu. Okay, now if we can choose, let's choose, or let's set rather v of u to 1. Okay, then we would have something like this, that f prime mu whole square would be into g mu would be equal to 1. So then g mu is actually, or rather f prime mu is equal to 1 by g mu, and then f prime mu whole square is 1 by g mu, and f prime mu is equal to g mu to the power minus half. So if we can choose if we can choose the function f such that f prime mu and this thing holds equal to g mu inverse, if this holds such that box holds, then we will have transformed, then we would have variance of u equal to 1, that is the fluctuation in the variances would be stabilized. Okay, and as a special case we have seen a few cases. All right, so if let's say this is the relationship that sigma square is equal to constant, then we don't need any transformation, because that actually corresponds or conforms to the assumptions of homoscedasticity. But if we see that sigma square is proportional to expectation of y, then what is the thing? Then sigma square is proportional to mu. Okay, so then g mu is actually mu to the power 1. Okay, so then f prime y is actually g mu to the power minus half. So this is actually what this becomes, mu to the power minus half, that is so from here f prime mu is g mu to the power minus half. So if f prime mu is mu to the power minus half, then fy is how much? It is integration mu to the power minus half f prime so f prime y would be equal to gy whole to the power minus half. Okay, so gy is actually minus y to the power minus half. So therefore fy will be integration of y to the power minus half dy. So this would be y to the power half. Okay, should be fy should be proportional to y to the power half by half. So 2y to the power half. So if I want to remove 2, then I can write this is proportional to this thing. So this is root y. Therefore the required transformation when we have sigma square equal to mu, then the transformation is actually fy equal to root y. So sigma square will be equal to mu when we have Poisson variable. Okay, and in that case, if y is following a Poisson random variable, then we will also observe whenever we are doing this normal probability plot, we'll observe a deviation. It will not fall on this line, it will be deviated to later points. Okay, so in that case we have to use this transformation and transform this to root y. And then we would fit root y on our x's, and then that way the variance of root y would be some constant. Okay, so this is how all sorts of transformations would take place. All right, fine. Now in the case where we have something like this case where sigma square is proportional to expectation of y square, or in other words sigma square is proportional to mu square, in that case we would have g mu as mu square. Okay, and then f prime y would be gy to the power minus half. So this would be this would be y. So therefore f prime y, if it is y, then fy will be equal to this will be okay. So from here, if we directly do this, that if so f prime y will be, sorry, from here this would be y inverse. So fy would be 1 by y dy, that is proportional to log y. Okay, so therefore when we have something like this, sigma square is proportional to mu square, then fy, the transformation, the required transformation is actually log y. Okay, so moving on, if sigma square is proportional to, let's say, mu to the power 4, then what do we have? We have f prime y equal to y to the power 4 and then f prime y would be g mu to the power minus half, that is mu to the power so g y minus half, that would be y to the power 4 into minus half, so this would be actually y to the power minus 2, and so fy would be proportional to 1 by y squared dy, so this would be proportional to 1 by y. Okay, and in that case the required transformation would be y to 1 by y, and then that would be fitted on the regressors. All right, so if we go back here, f prime mu equals to g mu to the power minus half, then f mu would be integration of g mu to the power minus half d mu, so this would be mu to the power so if g mu holds this form k mu to the power q, so then this would be k mu to the power q minus by 2 d mu, and that would be k mu to the power 1 minus q by 2 k star mu 1 minus q by 2. If q is not equal to 2, and this would be some k star log mu if q is equal to 2. So using this generalized formula, we can land up at this table. So let's say this is the relationship and this is the transformation. So if we have sigma square proportional to y, which is the case of a Poisson distribution, then the transformation is fy equal to root y. If we have an exponential case where we have sigma square is directly proportional to ey whole square, then the transformation is log y. Okay, if we have something like this proportional to ey cube, then we have fy equal to y to the power minus half. If this is proportional to ey to the power 4, then fy will be proportional to then fy will be 1 by y. And in case sigma square is proportional to this thing epsilon expectation of y into 1 minus expectation of y, in that case the transformation would be sine inverse of root y. Okay, and this situation will arise if the underlying distribution is a binomial distribution. Okay, so this is one form of variance stabilizing transformation. Alright, we also learned about a different form of transformation, which is a transformation to linearize the model. So the thing is, let's say if we have something like this, so if the model is like this, that as x is increasing, y increases exponentially, then the underlying relationship between x and y is something like this: y equal to beta naught e to the power x beta 1. Okay, now if we take log on both sides, log y would be log beta naught plus beta 1 into x. Okay, so then this model is actually linearized. Okay, so here the transformation is x remains same, but y will be log transformed. So this sort of models are known as log linear model. So this is actually nothing but a log linear model. Okay, the next use case that we learned was this. If we have a model like this, that is y equal to beta naught x to the power beta 1, then we would have log y equal to log of beta naught plus beta 1 log of x. Okay, so this transformation, if we have a variable of this sort, then this transformation is actually known as could be known as the log-log transformation. Okay, so you transform y, you transform x, and then this is the linear model which arises as a result of it. Okay, and if we have something like this, okay, where this is the x value and the y value goes something like this, and we are modeling y equal to log x type of situation. So this would be y equal to beta naught plus beta 1 log x. Then we'll only need to transform x to log x. Alright, and another situation that could arise is this one, where we have something like this. As x increases, y sharply decreases, and then this is the graph and this is how it looks like. Then we can model it as y equal to x by beta naught x minus beta 1. So if we take 1 by y, that would be beta naught. So if we take 1 by y, then that is beta naught minus beta 1 into 1 by x. So then for this sort of a scenario, y would be transformed to 1 by y and x should be transformed to 1 by x. And then we can go about doing these sorts of transformations. All right. So this was all about week 8. So the last part is, how do we determine which transformation to apply? Okay, so for this thing we need to go back to the residual or normality plots. Okay, so if the residual plot, this is equal to 0, shows some kind of pattern, okay, so if we consider a simple linear regression, let's say, okay, so in case of a simple linear regression, instead of plotting EI versus YI predicted, we could also plot EI versus XI. And if we see some nonlinear pattern, then we can go and make it into a we can transform the x's, okay, we can add instead of linear terms we can add x to the power polynomial forms of xp, okay, but this is not always possible. In case of multiple linear regression, we are going to fit EI versus YI, and even if there we find some sort of non-normality in the if we find some sort of patterns forming here and there, we could go ahead and plot the scatter plot between y and x, okay. So again, in multiple linear regression we will have multiple x's, okay. But the cases that we have shown over here, those will work with simple linear regressions only, okay, the transformations that we just demonstrated, okay. So how do we do it? We plot the scatter plot between y and x, and we look out for patterns. So suppose if this is the x and this is y, then something like this or this would imply that y equals to beta naught x to the power beta naught 1. Then we'll take log on, then the transformation would become that y prime is log y and x prime is actually log x, okay. Again, if we find something like this, that the scatter plot is like this, or this is somewhere like this, then this would be indicative of y equal to beta naught plus beta 1 log x, okay. So similarly, so on and so forth. If we find if we do find something like this that we showed over here, then the underlying assumption would be to make it residuals. So all I want to say is that which transformation to apply. If we are doing these transformations taking log or inverse to linearize, then that would be the pattern would be visible from the scatter plot between y and x. Okay, but if we see some deviation from normality, so let's say if we draw the normal probability plot, and we see that this thing, ei versus pi, this is the graph, and it's something like this. Okay, or something like this, not at all falling along these two lines, then we suspect that okay, the underlying distribution is actually non-normal, and then we inspect what it could be. Okay, so based on the mean and sigma square, we would have to take a call. Okay, so we can get estimates of mean and sigma square, and then we can sort of plot it, or make a guess about what could be the underlying relationship between sigma square and mu, and then once we are sure about the underlying distribution, we could actually use these sorts of transformations to make the variance stable. All right, so so if there are no more questions, thank you so much for joining, and I'll see you in the next class.